Hello, miss. Let's go. Yes. Sorry for the delay. I was eating something. Yeah, let's go. Sorry. Yeah.
Yeah. Let's start. So,
Today we'll talk about quantization. No, we'll talk about power spectral density.
in the last lecture, we discussed about it. That is, yes. Just give me 1 minute.
The internet is
Network
not very
is
stable.
not.
Yeah.
Yeah, is my screen visible?
Yes, yes. The connection is loose.
Hello.
Oh, yes, I can hear you. Let's go. Yes.
So, let me start. Today we have to do power spectral density, encoding and power spectral density. So, let's start. Is my screen visible to you? Hello?
Yes, yes, it is visible.
Okay, so see, we were done with sampling, we were done with quantization. Now the third step is encoding. So in encoding, we have different schemes for encoding. For example, in quantization, we got some fixed number of levels, right? L1, L2, L3, L4, something like that. L1, L2, L3, L4. For example, we got these 4 levels. Now, in encoding, what do we have to do? We have to assign some bits for each level, right?
Yes.
So, what can we do? What are the possibilities? For example, let's say we have the 4 levels as, let me just take an example. Let's say you have -3, -1, -0, and 1. These 4 levels you have, okay? So what you can do is, in encoding, the encoder, this is your encoder. Now these 4 levels are given to the encoder. Now it's the job of the encoder how it will assign bits to each level. So one of the possible ways it can assign -3, 0, 0 to -3, 0, 1 to -1, and 0, 1, 0 to, or 1, 1 to 0, and 1, 0 to 1. So every time it will get -1, the encoder will assign it 0, 1. Every time the encoder gets 1 as the input, it will give 1, 0 as the output. Okay?
Yep. Yep.
Yeah. Now, how will we show it in the diagram? For example, these are 4 levels. Now, let's say the encoder is generating the output as 1, 0, 1, 0, 1, 1, 1, 0, 0. Right?
Yep.
This way, the encoder has some certain encoding scheme. Now, how to plot that encoding scheme? That there are many different line coding techniques. If you know about it, line coding techniques.
Yep.
And there are many line coding techniques. Let me take few of them. For example, you have polar signaling, and unipolar signaling. What is polar signaling? Do you have any idea? Or it is also known as antipodal signaling. Antipodal signaling.
I'm a little bit confused. Can you just talk about it? Can you elaborate? Like, is it like something with polar coordinate, or it's something completely different with that?
Polar means the like plus and minus. Here it represents both the sides, negative and positive. So that means
okay.
that means what will we do in polar encoding one, if you get bit 1, then you will assign, like, how will you transmit the signal? It is like here, if you are getting bit 1, so you will transmit a positive pulse like this, a positive voltage, let's say plus V. So plus V. And if you get
Okay.
0, you will transmit minus V. So if, let's say, one got 1, you will transmit plus V. If you get 0, you will transmit minus V.
Oh,
Again,
okay.
1, you will transmit plus V. Then again you got 1, let's say. Again, so you will transmit plus V, like that.
Okay.
This is your polar
Understood.
signaling. In unipolar signaling, what do we do? Unipolar signaling is, if you get bit 1 will be taken as plus V voltage and 0 will be taken as 0 voltage. So that means if you get 1, you will transmit plus V, let's say plus 5 volt. Then if, let's say, you get 0, then you will transmit 0 volt. Then let's say again you got 1, so V, again V, 1, 1, then 0, so 0, like this. Right?
Oh, yeah. Let me think. Unipolar, yes, 1, 0. Let me take a look. Let me take a deep look. Oh, okay. So there's no negative. This just flat.
Yeah, only 0. Means 0 bit means
Oh.
you will not transmit anything, we can say.
Okay, but so why do we have two different sampling, signaling? Why do we do that?
There are different signaling here. If you can see, the energy we need to, like, even if we are getting 0, then the energy we still need to transmit some energy. But here, what is the advantage? You don't have to transmit anything if you get 0. Then if you are sending nothing, the receiver will understand that, okay, it was the 0 bit. Okay, but there are some advantages and disadvantages of both of them, right? So basically, there are other signaling techniques also. They are all are application based. Like, some techniques are useful in a particular application, then other is useful in other application. Okay.
Yep.
No one technique is good or bad.
Okay.
Wait, my screen is hanging. Just give me 1 second.
Sure.
I don't know what's wrong.
Yeah, maybe we can restart. We close and open. I'm not sure. Maybe you can do that. Or
Yeah. Let me share the whiteboard. Maybe it will work fine. Okay, see. So we were talking about polar and non-unipolar. Now, see, there are two more signaling techniques. One is return to 0 and other is non-return to 0.
yeah, I can't see your writing. It's just white.
Wait. It's stuck. Yeah.
Okay. Now I can see the pen. Yeah.
So now, second one more is return to 0 and non-return to 0.
Okay.
Non-return to 0. This is also known as NRZ, non-return to 0, and other is return to 0.
Okay.
Return to 0 is denoted as RZ. Now, this non-return to 0 and return to 0 can be both, either unipolar or bipolar. Okay.
Yeah.
But what is the basic meaning of return to 0? It means there are two cases in this also. one is unipolar and another is bipolar. Similarly, here also two cases, unipolar and bipolar. In unipolar means we will again the same thing, plus one is assigned, one bit one is assigned plus V and 0 is assigned 0 volt. But the difference is this, that 1 will not be plus V for the entire bit duration. For example, initially it was like this, no, 1 was like this and 0 was like this.
Yeah.
If this is your bit duration, TB. What is TB? TB is the bit duration. Now, in unipolar, non-return to 0, it will be same. Means it will be 1 only for the entire bit duration. It will be 1 only for the entire bit duration. But in case of return to 0 and unipolar, this thing is still same. But what is different is, if let's say this is your bit duration, second bit duration, this is again 2 TB here, this point. Now this, if you are sending 1, then you won't send plus V voltage for the entire duration. What will you do? You will send plus V for some duration and then it will return to 0, something like this. Yeah.
Oh, okay.
This is 1, and then for 0 it is still same. 0, for 0 it will be 0 only. But for 1 it will return to 0. Once it was, initially it will be plus V, then it will return to 0. Is that clear? These are just
Not very not very
Yes,
clear.
sorry.
Okay, so what? So basically, unipolar. What's the difference? I mean, none return to 0 and then return to 0.
See,
I mean, I can just see. So is it based on TB or something?
TB is just like here, you have to send the complete voltage V for time TB. Here we are trying to reduce that energy. So we will not send the plus V voltage for the entire bit duration. We'll
Oh, okay,
send,
only half,
understood?
like half or quarter. Okay, so why
Not
is
half,
that? Why we?
just to reduce energy consumption.
Okay, reduce energy consumption.
Yeah. We'll
So
need
basically,
more
return.
energy to,
So
we'll need
basic.
yes.
So basically, return to 0 is often used because it saves energy, or it's
Actually, again, it is depending. It depends on the application. Okay, so if I'll go into that much detail, then it will be difficult for us to, stay focused on the track. Okay.
Okay.
Yeah, you just need to know that it is just for saving energy, and no, nothing is good, nothing is bad here. It completely depends on the application. What is the requirement? Based on that, we have to choose anyone.
Okay.
Okay. Yeah, and you will be given this to in your question or something like which scheme they are using: return to 0, non-return to 0, unipolar or bipolar.
Okay.
Yeah. So this is unipolar. Now, same thing will happen for bipolar. One here it will be plus V, and for 0 minus V. But if it is non-return to 0, then the same thing means 1 plus V for 1 and minus V for 0. You will send for the entire bit duration TB.
Okay.
But here, what will happen? For 1, it will be this is TB, this is 2 TB. For the bit duration, let's say if you have to send 1, then for some time you will send plus V, then it will return to 0. If you have to send 0, then you will send minus V for some duration, but then it will return to 0. Means this was minus V for some duration, then it will return to 0 like this. And this, how much is the duration? This can change. Not necessarily this will be half of the bit duration. Okay?
Yeah.
It can be anything. And let's say we call it T on. T on means T on. T on means the time for which it is 1. Means the time for which we are sending something.
Yep. Oh, the time we're sending something. Okay.
Yeah.
This graph is the second, the bipolar return to zero graph is very interesting.
Yeah. So here for one, it is like V, then return to 0. For 0, it is minus, this is plus V and this is 0. Minus V and then return to 0.
Oh, okay.
Like this.
Okay.
This is V, this is minus V, this is 0, this is 0. Something like this.
Okay. Okay. I can follow. Yes. Understood.
Okay.
Somewhat understood. Yes.
Okay. Next. After this, so now you see, using this binary data, the example which we were taking, in that example, wait. Okay. After this, now you see, let's say we were sending the data like this. I gave you the example where I assigned -3 was assigned 0, 0, and -1 was assigned 0, 1, 1 was assigned 1, 1, and 3 was assigned 1, 0, right? This example I gave you 4 levels and the bits assigned to them, right?
Oh, can I ask why -3 is 0, 0? Why is it assigned this way? Should I follow a binary or it's a
This is binary. This is binary. These are binary bits. This is the job of the encoder. No? It can assign using any technique.
Okay.
Just unique representation. Okay. No, it doesn't matter. No? You assign, what do you assign to this? As long as the encoder and decoder know, it will encode and decode. It's like setting a code that, like, if I say this, you will understand this. If I say this, you will understand this. So it doesn't matter how do you code it. What matters is whether you are understanding it or not. Right?
Yep. Oh, okay.
If let's say encoder is saying that I am assigning 0, 0 to this level -3, then here will be the decoder. Then this encoder and decoder has already this encoding scheme with them. So the decoder, once it will receive 0, 0, it will interpret it as -3. So no matter if you assign 1, 0, it will, if you get 1, 0 here, you will get, it will like decode it as -3. Got it?
Oh, okay. So I can set whatever I want. It doesn't really matter. So, but I just need to follow that the decode. Okay, understood.
Yeah. Now next thing was, okay. Yeah. So let's say if we are sending using that scheme which I just told you, 0, 0, 0, 1, 1, 1, and 1, 0, -3, -1, 1, and 3. Right? So if I want to plot it, I can plot it like this. T. If the encoder is sending 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 0, 0. Encoder is sending like this. So how will I plot this? So 1, 1 means 1. So voltage level is 1. For how much time? For 1 bit duration. For time TB. This is 1 volt. Then 1, 0, 1, 0 is -1. So -1 for next bit duration. Then 0, 0 is -3. So -1.
Did you make a mistake? It's -3, isn't it?
Sorry.
Did you make a mistake, or it's you didn't make a mistake? 1, 0 should be 3, isn't it?
Why? What's wrong in that?
1, 0 is 3, isn't it? So I'm confused. A little bit confused.
Okay. Yeah, sorry. 10 is 3,
Yeah.
not minus 3.
Yeah. I was like, I was confused. I was like,
Okay, yeah.
yeah.
So it will be 3. So it will be like this. It is 3, then 0 is minus 3. So minus 3 is here.
Okay.
So will be something like this. 3 TB. Then 0, 1 is minus 1.
-1.
So minus 1 is here. Then 1 is 1. So 1 is here. Then 1 0 is minus 3 again. So something like this will have
Yep.
the wave, right? Now you can see this is what okay, this is not bit duration, by the way. Is it the bit duration? Can you see one thing? From here to here, is it the bit duration? Because there are 2 bits. This is the duration for 2 bits, not for single bit. Bit duration is the duration for 1 bit,
Yep.
right? So this we simply represent by T, which is symbol duration. So this is
Okay.
2T, T, 4T, 5T, and so on. So T is your symbol duration and TB is your bit duration in which 1 bit is sent. So bit duration.
Oh, okay.
And there are other parameters which you should know about. What is the relation between them? Simple relation will be T is equal to number of bits in a symbol N multiplied with the bit duration will be TB, right? Is this thing clear?
Symbol duration, yep. Bit duration, yes. Clear, yes. Symbol
Yeah.
duration, bit, yep.
Then we have bit rate. What is bit rate? How many bits are sent in 1 second? So it is bits per second. BPS, we write it as BPS, bits per second. And it is denoted by RB. And RB is equal to 1 over TB. 1 by bit duration is your bit rate. Okay.
Okay.
Then 1 by TB is simply we can write from here what is TB in terms of symbol duration. TB is T by N. So 1 by TB will be N by T.
Yep.
Is this clear? Okay, then symbol duration is T. Then what will be symbol rate? We denote the symbol rate by D. And this is equal to 1 by symbol duration, T.
Oh, okay. Okay.
From here, can I write? Okay, this is one important result. But from here, can I find out the symbol rate in terms of RB? This implies T will be equal to, T will go on the other side, will be equal to N divided by RB.
Yep.
So 1 by T will be RB by N.
Oh, also one, so it's RB over N. Oh, okay. Simple rate. Okay. Interesting. Very interesting. Wait, let me digest a little bit. RB is 1 over TB. So yes, T. So it's all interconnected. So T is equal to symbol duration, and then there was like number of it, and then there was like the bit duration. So it's just like RB, you play around with it. So 1 over TB. So so symbol rate, symbol. Can I ask why symbol rate? Symbol rate, yes, symbol rate. Okay, symbol rate is T or 1 over T.
How many symbols you have? Symbol is this whole, like how many bits are combining. Symbol, you can take it as level. Means level.
Oh, level. Okay.
Level.
Okay.
Yeah. This whole is your
Okay.
level. How many bits are representing the level?
Okay.
So level will not be the correct word. This is basically symbol is what? This is the word which is made up of bits.
Yeah.
This is one symbol. This is another symbol. This is third symbol, fourth symbol.
Okay.
So that means multiple bits will make a symbol. So n bits will make a symbol. If we are encoding a level with n number of bits, then that n bits combinedly is known as the symbol.
Okay.
That n bit combination is known as a symbol. So it's very simple. Okay. Yeah. So all these points are clear so far?
Yep.
Okay. So after this, to make it more clear, let me take just an example where you have to apply these points. No, pulses with the correct one. Yeah. Quaternary means 4 symbols. Quaternary pulses means what? Number of symbols are 4 or number of levels are 4.
Oh, 4. Okay.
Yeah, think about it once and tell me what should be the answer.
Is it 1 over 9,600? 1 over 9,600. Oh, I'm wrong.
What is that?
The bit rate.
The bit rate. First of all, you just see the units. Is that correct?
Okay, per second.
Bits per seconds, right?
Yes.
The bit rate should be in terms of bit per seconds.
Yes. So what's the bit rate? So bit rate is 9,600.
I'm quoting here pulses means what? Pulses means symbols.
Symbols, yes.
Right? So symbols, that means what they are giving you. They are saying, oh, sorry.
Okay.
They are saying 9,600 is your symbol rate. Symbols per second.
Yep.
Per second means what? This is your symbol rate.
Yep.
If you have symbol rate, you have to, how do you find out the bit rate? We had the formula. Symbol rate D is equal to, in terms of bit rate, it is RB by N.
Oh, so yes, 9,600 divided by 4.
RB by N. For modulated transmitting pulse using binary signaling.
Binary is 2 bits, right? So it's 2, so it's divided by 2.
No. Binary means only 2 bits you have to represent a symbol. So one symbol will be, this N is the number of bits per symbol.
Yeah.
Right? So binary means you have only 2 levels. Number of levels are 2.
Okay.
So number of bits will be 1. Just note it down. Binary signaling means you have 2 number of levels only. Number of levels equals to 2.
Wait, please.
Yes. And number of levels 2 means find out the number of bits.
Okay, so the number is equal to 2. Okay, understood. Binary signaling, yes, number level equals 2. Okay.
Yeah. So what will be the number of bits per symbol? Number of levels are 2 power n, and n is the number
Yes.
of bits. So if this is 2, so what should be the value of n?
2. 1.
1. 1. So n is 1 here. So n is 1 means it is equal to RB. So RB will also be equal to 900, 9600 bits per second. So always remember this thing that for a binary signaling, if you have the number of levels as only 2, in that case, bit rate and symbol rate will be same. Always.
Okay.
D is always equal to RB. Okay.
Oh, okay.
Please note it down once and then find
Yeah.
out the next one.
Is it 4800? Hello. I think I'm correct. It's a 4-bit, isn't it? Quadrantal.
Levels. Again, I will tell you 4 symbol. Pulses means symbols.
Yeah,
Quaternary
symbols.
symbols. So that means
Yeah.
number of symbols are 4.
4, yes.
Number of symbols are 2 power n.
Yeah.
2 power n is 4. So what will be the value of n?
2. So divided by 2.
Yes. So divide by 2.
2 is
So
4800.
no. 9600 equal to RB by 2. So 2 will be multiplied on that side to find RB.
Oh, shoot. Okay.
So it will be 19,200.
Let me digest. Let me absorb. Oh, okay. It's 19,200. Okay, understood. Understood.
Okay.
Yes.
After this, next you see. Okay, in this question only, find out the symbol duration and bit duration also. Wait. Mhm. Yeah, symbol duration and bit duration.
Beg your pardon? For this question?
Yeah, for this question only, find out the bit duration and symbol duration also.
Okay. Speed duration, symbol duration. I'm not sure, is it 1 over something or is I'm wrong again?
Let me show you it.
Yeah.
See it from here.
I just need to jot this down. I mean, just T. Is it 9,600? It's still the same. It's 9,600.
Duration. It is
Yes.
what? See, the relation is here.
Yeah.
So
RB is
how is it same? TB you have to find. TB is the bit duration, no? So TB is 1 by RB.
Yep.
RB is 1,99600. So TB will be 1 by 9600.
Yep. Yep.
Yeah, so that is your answer. Right?
Yes. Yes. You're correct.
Yes. So, and symbol rate, sorry, symbol duration, T.
So T is 1/D. So 1/T. 1/D. Yes. 1/D. But 1/D is equals to N/RB.
Yes.
Is it?
Yes. And
So
what is N?
N is 2, right?
Okay. For which case it is 2?
For second case.
Yeah, for second case it is 2. For first case it is 1.
Yes.
So
So it's
accordingly you will, yes.
2/9,600.
Yes.
Oh,
So that
okay.
will be your symbol duration. Is that clear?
Okay. Yes. Yes.
Okay.
Yes.
So this way you have to relate bit duration, symbol duration, bit rate and symbol rate. And you can see very easily this thing. See, if you have only one bit per symbol, like either you are representing the symbol by 1 or you are representing by 0, then obviously the symbol is containing, you can see 1, 0. So you can see the number of bits in a symbol is 1 only, right? So this will be your bit duration. And the symbol duration, both are same only. Symbol is containing with 1 bit only. If it is having more than 1 bit, then obviously the bit duration will be different from the symbol duration. Right?
Yep.
Yeah. After that, we have something called as duty cycle. What is duty cycle of a pulse train? You can see one thing. If let's say this is the symbol duration 0 to t. Okay, and this is not like this is not 50-50. It was one. It was 1 for some time, then it became 0. So you can see this is your T pulse width. In the whole symbol duration, this was the pulse width. Or we can say on time. T on time. T on. It was on for only this much of time. Rest of the time it was off.
Yep.
So what will be the duty cycle? Duty cycle is defined as the percentage of time it was on. That means T on divided by T multiplied with 100%. This is the way the duty cycle is defined. It generally it tells you for what percentage of time it was on, right?
Okay.
So if I give you, let's say the duty cycle is 50%. If duty cycle is 50%, then what will be T on? T on will be 50 equal to T on by T multiplied with 100%. So from here you will get T on as 50 by 100 times T, which is T by 2. Means duty cycle 50% means it will be on half of the time T. Right?
Oh, okay. Okay.
But if the duty cycle is different, if the duty cycle is 30%, then what will be T on? You find out what will be T on in that case. Or we also call it as pulse width. T on or pulse width. Both same. Both have the same things.
Is it 60? Yeah.
Sorry?
Is it 30%? So it's 60 divided by 2, so it's, I think it's 60.
Divide by 30. Here you will
30,
put
yes.
equal to T on by T multiplied with 100. So
Yes.
100 will go on the
Oh,
other side.
yeah. Oh, okay. So it's a T equals to 1 over 3. T equals to 3.
0.3 times of T.
3. Yeah.
So this way, if you are given T on, sorry, if you are given T, the time period is given to you, then you can find out the time on time or pulse width
Yeah.
easily. Okay.
Okay.
Then how the time period is related with the frequency? 1 by F.
Yeah, 1 over F. Yes, so T equals to 1 over F.
Yes, so we can write where T over 1 by F is equal to T.
Yes.
Both are the same thing. So this
Yep.
you have to remember. Sometimes,
Okay.
sometimes they will give you duty cycle frequency and you have to find the pulse width or the time on time.
Oh, okay.
Yeah. Okay, let me give you an example now for applying this concept. The duty cycle of a 5 kilohertz pulse train is 60%. Find the pulse width. Try it once.
Frequency is 5 kilohertz.
Yes.
The duty cycle is 60%. Is it is it very small? It's 0.00012. Because I think of it as frequency is 5 kilohertz, and then the duty cycle is 60%. So T0 over T is equal to 0.6. And then the frequency is obviously 1 over T, so T is equals to 1 over F. Because it's a 5F, so it's a 1 over 5K. Sorry, 1 over 5K, so it's 0.0002, and then you just type two things times together, you get a width.
Okay, see. So our duty cycle is 60% equal
Yes.
to T on or the pulse
Yeah.
width divided by T times 100.
Yes.
Here 1 by T is F. So 1 by T I'm writing as F.
Yep.
So you can just simply find it out. Shift both of the things on this side. So 60.
Oh, wait, did I make a mistake? 60 is equals to time F, yes.
So
Yeah.
60 over
60 divided by 100 times 5K. Yeah, it's the same numbers I get. So 1.2 times to 10 to the power negative 4. Yeah.
whatever you get, that is your answer.
Yeah. Okay, understood. I'm getting there, miss. I'm getting there. I just need to get there slowly,
Now, this was so this was a general concept for a pulse. Okay. Now, in
Yes.
our case, how is it applicable? So this is because We were talking about return to zero signaling, right? RZ.
Yeah.
So in RZ, I told you that when you are sending bit 1, it will remain 1 for some time, then it will return to 0. But how do we know for how much time it will remain 1? How do we know? That will be told with the duty cycle. They will tell you the duty cycle is this. That means they are indirectly telling you for how much time you have to keep the signal 1 and then make it 0. If you have to send
Okay.
bit 1.
Okay. Okay. No, I'm digesting. I'm trying
Yes.
to learn. Yes.
Okay. So that means in our case, when we are talking about, especially it is applicable to return to zero signaling. So the same concept how to apply in RZ signaling is, we know like for 0 bit, there is nothing to learn. There will be nothing sent, right? But for if 1 is sent, then the bit will be 1 for some time and then 0 for the rest of the time. So this is your TB. The bit, sorry, not TB, the symbol duration. Okay, this symbol duration.
Okay.
Then this much is your T on, and duty cycle will be given to you. You will just relate all of these parameters, and this T is related with T is the symbol duration here.
Okay. Can
And
we
it
take a break? Can we take a break? I think I need a break. I need a 5 minutes break. Do you mind?
okay
I'm
then.
really tired. Can we just stop? Can we just go back after the
Fine.
break? We just repeat the whole thing. Thank you. Yeah, just give me a few minutes break. Thank you.
So
Hello, I'm back. Yes, let's go.
Okay, let's continue.
Yeah, let's continue.
So, yeah. So I told you that this is for RZ signaling how to apply the concept of duty cycle. So when we are sending a symbol, like let's say bit 1, so it will be symbol duration divided 1 by symbol rate. Got it? So 1 by
Yep.
D. This is related how like this. Then how did we write the symbol duration in terms of the duty cycle? So T on by T into 100 is equal to duty cycle. So you can just relate these two relations. These two things can be related. Okay.
Yep.
Now the next thing we have is PSD, power spectral density of a pulse train. Okay, before that, let's deal with the question which is given. There are two parts of that will be done now. So just open the question once.
Yes, I'm opening the question now. I have it printed out. Yes, okay. So it's the binary unipolar RZ encoding scheme is used in a digital communication systems. Consider a random data stream consists of a binary of 1 and 0 occurring with equal probability. Assumes that at 8.3 kilohertz, 8% duty cycle rectangular pulse train is used. Calculate a PSD, power spectral density, of the encoded signals.
Yeah, PSD we haven't done yet. We'll do it. Second question, see the bit rate and symbol rate you have to find. So that you can do.
Okay.
See, so they are giving you unipolar RZ. I told you RZ is this. And unipolar is also this. Unipolar simply means 0 is to be assigned 0 volt, right?
Yep.
Yeah. Then they are giving you the frequency. Frequency is given to you. That means time period is given. So time period will be 1 by frequency, which is 1 by 8.3 K.
Yep.
So this will be your time period. Now, if you, and the duty cycle is given as 8%.
Yep.
So 8% is the duty cycle. Then what do you have to do? Yes. So you have to find out the bit rate and the sorry.
Yes. I'm still listening. Yes.
Yeah. So you have to find the bit rate and the symbol rate.
Yep.
So how do you find out?
So it's 0.08 times 1 over 8.3 kilohertz. I assume that's the symbol rate.
That's the symbol rate.
Oh, so, no, sorry, that's the bit rate.
Can you write it and send it to me? What you're saying?
Yeah. I'll try to do that. Yeah.
Yeah. First of all, tell me, will this duty cycle be used when you are finding the symbol rate or the bit rate?
Yeah, it will be used.
How? You have to find.
Yeah, the T0, right? I have to find.
Yes. Find out. So you have to find out T on. And once you'll have T on, you can just take the reverse of that. 1 by T on will be your symbol rate.
Yeah, yeah. So it's 9.63, times 10 to the power of negative 6.
Okay,
The TO is equals to 638.
Okay, so T on will be duty cycle by 100 times T. T is this. So that will be your T on. And if you have T on, then you can find out the bit rate. Bit rate
Yep.
will be reverse of it. So 100 into 10, 8 power 8.3 into 10 power 3 by 8. This will be your bit rate. And because this is a binary scheme, so the bit rate and symbol rate both will be same only. So this is your bit symbol rate also.
Yep.
Understood?
There's 103750. Maybe you can verify it. I think I'm doing correctly. So it's 103.75 kilo.
Wait.
And then that one is 9.638 10 to the power negative 6.
8.3 is 0.963. 963 multiplied with 10 power minus 5. So you can write 9.63 microseconds.
Yep.
T on is this. Now bit rate is 1 reverse it. 1 divided by this. 1.96 something. So it will give you 0.103 times 10 power 6 megahertz.
Yep.
That will be your bit rate. And the symbol rate will also be same.
Yep.
Yeah. So this was the second part. Now you have to find out the first, second, and the last part. For that, let me continue.
Yep. Yeah. We'll continue. Yeah.
Okay. So for this, there are two things. Like either we can use the direct formula. I can tell you what is the formula for the PSD in binary signaling. Other way is to do the complete derivation, but it will take a lot of time. Let me first show you how much, because it has some prerequisites also. You should know about random variables. You should know about autocorrelation function. Okay. And also you should.
All those things. Yes. Yes. Yes.
So all those things you should. Okay. You also need to know about
Probabilities. All those things. Yes.
the
So basically,
yes.
yeah, it can be very complicated. Yes. But I might ask you to go into those later on. But yeah, we'll do this PSD first. Yeah.
Okay, so let me just tell you how to do PSD. So in general, for any signal, we have the formula for PSD, which is, wait, PSD of any random pulse trains is given to you. We derive it, but the final result, let me tell you. What is the final result? It is this. G of F is equal to GS of F is equal to magnitude of V of F whole square divided by T summation. L goes from minus infinity to infinity. R of L into e power minus j 2 pi L F T. Let me tell you what are these parameters. So first of all, you will have a set of symbols, right? We have a set of symbols which is represented by AN. So wait. AN is your set of symbols. Here you have all the symbols. The levels basically L1, L2, L3, L4 up to Ln. The levels which the quantizer gives you. Those
Yep.
levels will be here. Then what is RL? RL is the autocorrelation function of this AN, which is expected value of AN multiplied with the shifted version of AN. This
Yep.
L and this L is same. Okay. Then
Yep.
this is done. RL is done. What is F? F is, you know, the frequency only. T is the time period. And VF, what is VF? VF you need to know about. So VF is the frequency domain representation of your pulse train.
Okay.
So VT. VT is your pulse train and VF is its frequency domain representation. For example, how do I tell you VT? Wait. VT is what? VT is the rectangular train. Let's say if this is like this, the time period is T, means the width I'm talking about. T on I'm talking about here.
Yep.
T on for the pulse is T on. This is your VT. VT versus T, which is a rectangular pulse train, magnitude is 1. Oh, not necessarily 1, but later on it will become 1. Now, this VF is the frequency domain spectrum of VT, which will be sync function, if you know.
Yep.
Right? You know, right? That the frequency domain representation of a rectangular pulse is a sync function.
Oh,
So
yes.
here,
Something like that, yes.
yeah. So a basic rectangular pulse, if we take V of T, we take as rect of T by T. This is the mathematical representation of this pulse.
Yep.
And then what will be V of F? V of F would be T times sync function F times T. T means T on, sorry, T on.
Yep.
So this is about VT and VF. So in general, this is the general function. Now, if we specifically talk about multi-level unipolar NRZ, what is that? Let me tell you. For multi-level means number of levels are 2 power n. Multi-level unipolar and NRZ or RZ. But we need for RZ, no? What do we need for NRZ? In the question, what they are asking you? RZ. Okay, we have RZ.
So it's because it's a 1 and 0. So it's a binary.
Wait. Okay, unipolar RZ we have.
Yes.
So for unipolar, wait. For unipolar RZ signaling scheme, we have the relation V. Okay, the relation will be same only. This relation only will hold true. But now you have to put V of F as this into this.
Okay.
So what will you get? GS of F will be, and in case of, okay. So if you will use V of F in the expression, then the final result which you will get is this. Okay, it will be very big relation. So let me see the final one. What will you get? Just put the value here. So wait, let me share my screen with you guys. And in the book, let me show you because it is a very big relation. Can you see my screen?
Oh, yes.
You can see here for unipolar RZ code, they are assuming the 50% duty cycle, but it is not necessary, it will be 50%. So the pulse width will be TB by 2, right? For
Yep.
pulse width will be TB by 2 if you have 50% duty cycle, but we will not assume it to be 50%. So instead of writing TB by 2, we will just write T on. So this will become T on. And here also you will get TB by 2 as T on. So RVB will be, VF will be T on multiplied with sync of T on times F. T on, you have already calculated in the question, which was given to you, right?
It's 9 points. I believe it's 9.638 microseconds.
Yeah, whatever that value was, that will be your T on. Then the spectral density for the unipolar RZ scheme will be calculated using this relation. Just replace TB, okay, what they are assuming TB as TB by 2, they are assuming now. So just put TB as 2 times of T on in this relation.
Okay.
And you will get your answer. Here, and here you have to put, and here you have to put. Or you can just use the simplified relation also, which is this one. Instead of TB, use 2 times T on, and T on you know the value. Understood?
Now T on is how much? T on is 9.6. Oh, okay. But how do I press calculator with sync function? Do they have sync function on calculator?
Sorry?
Do they have a sync function on calculator?
Sync function what?
They don't have sync function on calculator.
Oh, but you don't have to calculate. Why do you need to calculate it? We have to find the relation for the spectral density, right?
Yeah, but they're asking to calculate the power spectral density of the encoded signal. Or I was looking at the question. Okay.
Calculate means this only. Calculate means they're asking for the expression only, no? It will be a function of f. You can see here.
It's just the expression, is it? So I just plug in the numbers and then do.
No.
Yeah. So so I don't have to. Oh, okay. I don't have to. And how about the length, the L? The L, I just keep the L.
Variable from -infinity to infinity.
Oh, the variable. Okay, it's just a variable.
Yes.
Oh, okay. So it's the TB. The TB is the number. The TB.
From here you can see one thing. You can use this relation also. Sync L by 2 is 0, except means now what they are doing is, for this relation, they are doing something. Sync L by 2, they are doing something.
Yep.
For sync L by 2, they are telling that sync L by 2 is 0, except for these values. So if you will put it 0 here, it will become 0. So that then you will have only this much thing will be left. So now this is your simplified relation.
Okay.
Understood?
Okay. Yep, understood. Somewhat understood, yes.
No, wait. Not only this much. Because there will be, you have to do it. See, it will be 0 for plus minus 1, 3. Means here for the odd values, it will be 0, but for the even values, it will still remain. There will be some still value, right? Like for 2, 0, 2 plus minus 2 plus minus 4, it won't become 0. So for those values, they are considering the summation a square by 16. Then for these values, it is right. They are writing it.
Okay.
So just you can either keep it in this form or this form, whatever is convenient. Okay.
Okay.
So this way, this was the expression for PSD. Now, next part. Then the third question, I think they are asking you the first null bandwidth. So, sorry, what is first null bandwidth? First, you should know about that thing. So the null bandwidth means if you know this shape of the sinc function, magnitude of the sinc function, it varies something like this.
Oh, yes, it is something like that. Yes, okay.
Right? So what is the first null bandwidth? This is the frequency domain I'm talking about. And this is the magnitude. Now you see the first null bandwidth means this much. It is becoming 0 over here, right?
Yep.
So first null bandwidth is the bandwidth from 0 to that point where it is going for the first time.
Yep.
Just wait. Yes. That will be your first bandwidth. And if you will plot this graph, they are asking you the first null bandwidth. So we have the formula for the null bandwidth, which is which is equal to your D. Wait,
Oh, okay. Wait. Is it correct? I don't think so.
Wait. For we are finding for RZ, no? It is confusing a little bit. We are finding for RZ. So yes. No. Just let me verify it once. Set return to 0, we have to find the null bandwidth. For NRZ, it is equal to D. Okay, for RZ, we have to just let me verify it once. It is, I think, 2 times of RB for binary RZ. Just give me 1 second. It will be 2 times of RB, the null bandwidth here. Because if you see the graph, let me show you the graph. After this, you have to plot the graph also.
Yeah, just plot the spectral density, yes.
Yeah, spectral density graph we have to plot, right?
Yeah.
So, let me show you. as you could see, it was a sinc function. So if you will plot that equation, which I showed you there, you will get a graph something like this. You can say this is
the
a sinc graph, magnitude of that, right?
Yeah.
So you can say this is spectral density of unipolar RZ signal.
Yep.
But this is for RB is equal to 1. Bit rate
Okay.
equal to 1. Okay. It will be for any other RB also. It will be similar only. You can say this axis is F by RB. Right?
Okay. Yes.
So if RB is not 1, that means this, if let's say for example RB is 2, then what will happen? Just this axis will be divided by 2. Means it will be if you divide the axis by 2, that means it will be stretched, expanded.
Oh, okay. Can
For
you show
example,
me what is it going to be look like?
Yeah, if we have x of t something like this minus 2 to 2, and if you want to do x of t by 2, how does it look? It expands. It becomes minus 4 to 4.
Oh, okay. Okay.
So same thing will happen here. This graph will be just expanded. 1 will go to 2, 2 will go to 4, 4 will go to 8, like that. But the shape and the characteristics of the graph will be this only. Okay, this is the plot of spectral density.
Wait. When will be? Can you just approximate? Like approximate what is it going to be like? 1 is going to be 2. Can you just plot a new point? 2 and then 4. And then 4 is going to be 8. And then how's that going to work? I can't see this. Can you show me? Can you spoon feeding? Can you spoon feeding me or how to plot the graph? I'm a little bit lost with like a stretch.
Okay, wait. See, we had this relation for unipolar RZ. Our relation for the unipolar RZ was this, right? This was the relation. Here we have a sinc function. Right?
Yep.
So basically, this is not possible for us to draw this graph by hand, but we can draw it using some software or something. Okay, but basically we know from the graph that it is a sinc function, summation of sinc functions. So this shape is going to look like a sinc function only. Only that we can tell, right?
Yes.
So yeah, if you want to plot the exact graph, then it is plotted using the software. And I just showed you how it will look. So sinc function is something like this. So it will going to look like a sinc function only.
Yeah.
But these points will be decided by the bit rates. Means where it will become 0, that will be decided by the bit rate. Why? You can see it here. Sinc, inside the sinc, you have a parameter TB. TB is related with the bit rate. Right?
Okay.
So if TB is related with bit rate, means this argument of sinc function is going to depend on the bit rate. So whatever the bit rate is, you can adjust the graph accordingly.
Okay.
Okay.
Accordingly.
Is this thing clear?
Yeah, so I assume it's gonna stretch it out.
Stretch, yeah, it will be stretched. Just simply these points will be shifted. It will look something more like this now.
Oh, okay.
Like this.
So it'll be like a little bit heavier. You can say it this way. Okay.
Like this.
Yeah, okay, sure.
Yeah, so this was all about the spectral density.
So that's the last plot, huh? That is the plot of stretch. Can I ask what's the first new bandwidth? I'm a little confused with that. I'm a little. You say that. Can you just explain that again? I wasn't paying attention just now. I lost the attention. What is the new bandwidth?
Null bandwidth. Okay, okay.
No bandwidth. Yeah.
Null bandwidth, you can see it here.
Yeah.
So null bandwidth is the bandwidth where, let's say this is your PST spectrum, right?
Okay.
This is your PST spectrum. Now you can see this spectrum is having some nulls. Nulls means zero, where the PST is going zero. So first null is over here, second null is here, third null is here, fourth null is here, like this, right?
Okay.
What they're asking you, first null bandwidth, they're asking you, right?
Yeah.
What they said null bandwidth. What did they say? First null bandwidth. First
Yeah.
null bandwidth means this is the null point. You have to take the distance of the null point from the zero. This is your first
Okay.
null.
Okay.
This is B null. Okay?
Okay.
Yeah. And null bandwidth, if I show you, is equal to 2 times of wait. For the formula of the null bandwidth, I'm a little bit confused. I'll confirm this after the class. Okay, it is RB or it is N times RB. I need to check that.
So it's RB or N times RB. Oh, okay.
Yeah. Just let me check that. Because here they might be saying it RB because they are finding it for bit rate 1. But for RZ, it is definitely equal to D only. I can, let me show you that result. You can see it here. Null bandwidth for polar NRZ is B null is equal to D.
Okay.
Which is RB by K. They are simply taking N as K. We are assuming it to be N, the number of bits per symbol.
Yep.
Okay. So this is for RB. This is for polar and NRZ, but we need for unipolar and RZ, right?
Yep.
Yes. So unipolar NRZ is also D.
Oh, really?
Polar NRZ is also D.
Okay, so basically this is the thing. This is
Same
the
only,
equation.
right? Because so same equation we have. So
So
most
it's basically
probably,
so basically it's D equals to RB over
over
K
N. Yes, equal to
over N.
RB over. Okay, this is what? This is nothing but you can see M is the number of levels. 2 power N is the number of levels. They are denoting it by M. So what
Okay.
will be N? They are taking
1.
log base 2 on both sides. Log base 2 on both sides. So what will this become? This will become N equal to log base 2 times M. So this is what they have written over here. Okay.
Okay.
So this is your null bandwidth. So if you have RB and you have N, you can simply find out the null bandwidth. N is the number of bits which you can easily find out, and RB you already found. So null bandwidth can be found using this.
Okay, now so what's M? M is 1, right? In this case, it's binary, so it's 1. I assume it's 1.
Binary is 2 in this case. Number of symbols 2.
Yeah.
This is 2 na, in binary.
Yeah. Also,
Yes.
M is 2.
M is 2, yes. For binary case. So what will be
Okay.
N? N will be log base 2 times 2. It will be 1.
So what should I put M here? So it's log 2 1 or log 2 2?
Log 2, 2, 2 na? M is 2. So why to put 1?
Oh yeah, log 2 and RB is I already calculated RB.
Yeah. RB
What's
only
RB? RB is a 1 over the TON, right?
bit rate.
Bit
1
rate,
over
yeah.
T,
It's
TB.
1 over T
Yes.
1 over TB, yes.
Yes.
What's TB, yeah? TB.
You can just go back and revise. We just did TB and T and RB, everything.
Yes, I know. It's just mixed up together. Yeah, I know. Okay.
So is this thing clear?
Kind of clear. It's a kind of clear. Yeah. I think so. Yeah.
Okay, you just need to see. There are so many things if we need to cover in one class. So obviously things will be mixed somewhere, but you have to revise it and it will become clear, more clear. Okay.
Yeah. But everything is recorded. I know. I'm aware of it. I'm gonna catch up. I have a lot of other things to do. I was like got distracted into other assignment and all those things. It's very hectic period for me, but
Okay.
it is what it is. Yeah.
Okay, so wait, let me take one more example to apply
Okay.
this thing. For other schemes also, you can just refer to the book if you need. Other things will be also in the similar way. Like polar NRZ, polar RZ. Some slight changes will be there, but it will be done in the similar way. Okay, so the question. Let me take a question which involves all the three things: sampling, quantization, and encoding. In a PCM system, the signal M of t is equal to sine 100 pi t plus cos 100 pi t is sampled at the Nyquist rate. The samples are processed by a uniform quantizer with step size of 0.75 volt. The minimum data rate of the PCM system in bits per second is. Just try to understand the question and do it.
a little bit tired. Can you just guide me through this? Yeah, I think the frequency is 50, isn't it? So there'll be is there a guard band? So I assume there'll be guard band. Or it's 2B, so it's 2F. Is it 2 times 50, so it's 100? Hello?
100. Yeah.
Yeah.
Nyquist rate is 100.
Yeah. Nyquist rate is 100. Aha. And the sample alpha C is step size 0.75. So is it going to be divided by 2? So it'll be top and bottom. So it's like 0.75 and negative 0.75. I assume it's going to be some. Am I getting there or I'm wrong?
Sorry?
0.75. So 0.75. So there will be top 0.75 and negative 0.75. Is it going to be something like that?
No. What is that? You have to find out the minimum data rate. Think about it. It's not direct.
I'm not sure.
See, they are asking you the minimum data rate. They are giving you the step size. Step size is given as 0.75. Sampling frequency, which you just found, it was 100 hertz.
Yes.
Minimum data rate of the PCM system in bits per second. What do they ask? What are they asking you? They are asking you the bit rate. RB.
Yeah.
RB
So
is
1 over FS.
Yes.
So it's 1 over SS is 0.01.
No, 1 over FS is not RB. Try to recall what was the formula or try to derive at least. If you have TB, you have FS. How did we derive the relation for bit duration, bit rate?
I'm not sure. Is it TS? Is 1 over TS? That's TS, isn't it?
TS you can find out 1 over FS.
Yes.
It is 1 over 100. So 0.01. If you
Yeah.
have TS, you know TS is equal to N times of TB.
Yep.
And TB is 1 times 1 by RB.
Yep.
So you have
Yep.
N by RB as 0.01. And here RB will be equal to N by 0.01, which is 100 times of N. But now the problem is you don't know N. How to find out N? Just think.
Quadrantal, isn't it? And so N is 2.
N is 2 how?
Because it's 2 to the power of 1 2 equals to 4 so it's N is equals to 2.
No, it's not given. It's in this case, it's not given how many samples are there or how many bits are there. But some information is given. See, let me just give you a hint. You have to try it by yourself. Delta is given, so you can find out using delta and the given signal. Just think how you can find out N.
Do this. I'm lost. I'm saturated, miss. I'm saturated.
Okay. See, just see. Let me just give you one more hint. Delta is equal to the range Vmax minus Vmin divided by 2 power N. And this is given as 0.75. You can see here in this relation you have N. So if somehow you can find out the range Vmax to Vmin, you can find out N using this relation, isn't it?
So but step size 0.75 is the
And
I
here,
don't know what's
let
I
me
don't know
do
what's
it.
V max of Vn.
M of t is sine 100t, 100 pi t plus cos 100 pi t. So this is like sine theta plus cos theta. So can you write it as, what is the magnitude in this case? If I multiply, generally if you don't know this thing, sine theta plus cos theta can be written as root 2 times 1 by root 2 sine theta plus 1 by root 2 sine cos theta. We intentionally write it like this so that we can convert it in a form. This is cos 45
What is this?
and this is sine 40.
Yeah.
So this
Yeah,
is
yeah, okay.
cos A sine B plus sine A cos B. So which is sine A plus B. So sine theta plus 45. We converted it like this. So now your M of t is root 2 times sine. Here theta is 100 pi t plus pi by 4. 45 means pi by 4. You can see the maximum peak value of the signal is root 2.
Yep.
Peak, V peak is root 2. So what will be the range? It will be from minus root 2 to plus root 2. So it is 2 times of root 2, right?
Okay.
This is delta equal to this by 2 power n. That is equal to 0.75, which is given. Now, what to do? You can take it 2 root 2 divided by 0.75 equal to 2 power n. Using this relation, you can find out n. You can see n is the only variable. So just solve it
and it's anti-log, right?
Anti-log. Yes. So you can write it as log 2 root 2 by 0.75 equal to n. So this way we found n. Okay.
Yeah, okay.
So if you found n, we can go back here. Just put n here, multiply by 100, you will get your bit rate. And this is what they were asking. All right. Hello.
Yes, I'm still here. I'm tired. Yes, I understand. Yeah, I'll try to watch back something.
Yeah.
I need to take some time off. Yeah.
Yeah. So just
Too
revise
tired.
it once and do some problems by yourself. Then only you'll be able to,
Yeah, I know.
all the things. Okay.
Yeah.
Okay then. So yeah, that's it for today.
Yeah.
We end the class.
Thank you. Go end the class. Thank you.
Okay then. Bye.